Hope you guys are enjoying the snow day. But tomorrow we're going to start sex-linked traits to kind of wrap up our genetics unit. So you see on the screen right now, this is an X chromosome, this is a Y. Notice how much bigger the X chromosome is. Remember, the X chromosome is something that all humans have, both male and female. So there has to be some important characteristics on there, some important genes that are coded in the proteins that we all need. Whereas the Y, nearly half our population, or close to exactly half of our population, doesn't even need the Y chromosome, and they get along just fine without it. So the Y is something that's known as TDF, or I think the SRY gene leads to a testes determining factor, which is what causes gonadal dysgenesis. Makes you male as instead of female. So genes are found on the X or Y chromosome are known as sex-linked genes. The X chromosome is larger and contains more genes, so males are much more likely to inherit a sex-linked genetic disorder. So if you remember back to last semester when we were talking about meiosis and things like that, do you remember why? Or the karyotype discussion we had before that even, during our DNA unit. Do you remember why males are more likely to have a sex-linked genetic disorder? That's right, because females have two X's and males have an X and a Y. So say, for example, you've got a female with one mutated X chromosome. Maybe this Fabry disease thing shows up on their X chromosome. Well, their other X chromosome is probably in good shape, so it covers or masks or dominates this faulty X chromosome they have. Males, on the other hand, what if they get an X chromosome that is coding for Fabry disease through some mutation or inherited disorder? Well, their other sex chromosome is a Y, which means there's nothing there to bail them out, so to speak. There's nothing there to cover or mask that X chromosome that's faulty. So, for that reason, males are more likely to have a sex-linked genetic disorder than females. So what are some examples? There's hemophilia. That's where your blood doesn't clot or scab properly. You see some illustrations here showing the platelets. Someone with hemophilia, their platelets are either, low in numbers, or they're messed up or faulty in some other way. So the big fear there is actually internal bleeding, whereas as we would get a bruise, maybe they would continue to bleed internally without rushing to the hospital. A lot of times these people wear a necklace or a bracelet, much the way a diabetic would. Right, there's muscular dystrophy. That's a degenerative muscle disorder. Surely you've heard of that before. Maybe seen someone. Maybe you've got a cousin with muscular dystrophy. There's color blindness, Fragile X, Wiskott-Aldrich, and Coffin-Lowry. And these are just a few examples of sex-linked genetic disorders. All of these are possible in females, but they're much, much more likely in males. And again, that's because of the difference in sex chromosomes. Remember, in humans, there's 23 pairs. The first 22 pairs are autosomes. The 23rd pair are your sex chromosomes. So let's talk about color blindness in a little more detail. Right? It's a generic term. It encompasses more than 99% of all colorblind people. There's red-green, there's red-blue, there's different forms of color blindness, but about 8% of all men are colorblind and only 0.5% of women. We've already gone over why. So this usually skips a generation from grandpa to grandson, with the mom being a carrier in between. A carrier, we're going to talk about that a little bit later, but this is why it would skip a generation, or at least seem to. That gene doesn't go away and then just pop up again. It's there, it's just not expressed for that one generation in between. So we can do a few color blindness tests. What number do you see here? Should be a red 12 inside of a green circle. Here's a red 26 inside of a grayish circle. Here's a 58, an 18, a 17, and this is a letter E. Sometimes you'll see a plate where you have to trace from one side to the other, or maybe it's a plate where there's different lines. You have to say how many lines there are in that circle. So if you'd like to try any of these, go ahead, pause it, type in this tiny URL. Remember, it's case sensitive, and you can go to an Ishihara colorblindness test and see for yourself. Or maybe if someone claims to be colorblind, you can see to what severity they are, or if they're fibbing. So you could use a pedigree. It's another tool, a chart used in human genetics to analyze inheritance of certain traits, especially in a family line. Whereas a Punnett square shows you the probable outcome of the next generation, a pedigree shows you what's already occurred from the present through the past. And this lets you track and see which traits show up more regularly, and lets you analyze patterns of inheritance instead of what probably will happen. You can see how it is tracked through a family. So here's a pedigree. You'll notice you've got squares and circles. Maybe some of you have seen something like this before. Everybody seems to have that aunt that's into genealogy. She goes to the courthouse to look through old deeds and look for old marriage certificates of great-great-great aunts and uncles and stuff like that. She's at the graveyard doing stone rubbings. Maybe you know what I'm talking about, maybe you don't. But there's different disorders, and you can see here different things are tracked. And this doesn't always have to be disorder, like a bad thing. Maybe these affected males and females all have, free earlobes instead of attached earlobes. Who knows? You could track any trait using a pedigree. So there's different symbols we're going to use to make our own pedigrees. A male is just a square, a female is a circle. Affected, this is a male with that trait. Again, it could be a disorder, it could be crypto, it could be anything. An affected female would be a colored in circle. Unaffected is just clear, a clear circle or a clear square. A carrier, you'll notice, is half colored in. That means that they have that gene, but that trait isn't expressed. So that gene is there, but it's not transcribed and translated because there's another version. In this case, a good X chromosome there that's going to cover up that faulty X chromosome. And that's why most carriers you see in sex-linked traits, in fact all, are going to be female. Crossed, remember from Punnett squares, that means you've got two individuals that swap genetic information. So you start with a square and a circle, a male and a female. You cross them with a line in between. That doesn't mean they're married. It doesn't mean they lived happily ever after. It means that they swapped some genetic info and had offspring. So offspring are going to be the lines that come down from this cross. Here you've got things like this. And that tells you that there's two males, and see how these originated from the same point? Those are twin girls. Now, with anything, there's dotted lines, dash lines, and different things you could do to show adoptions and, half brother and step brother and all kinds of stuff like that. Deceased, it's pretty easy. You just put a line through something. So if you look at any pedigree or family tree, eventually they all are deceased if you look far enough back. You'll notice that there's no carriers in this situation. So that tells you that this trait is a dominant trait, which means if even one allele shows up, it's coded for. And you see how these males are all affected. I don't see any carrier females or anything like that. So a carrier, first thing to write down, is an individual that is inherited an allele for a genetic trait, but does not display that trait, which means they are able to pass that on to their offspring, just they themselves, that particular gene isn't transcribed and translated because there's another allele there that's more dominant, and that's what's expressed. So they do have the allele, they just can't pass it on. So these people are always heterozygous. They have that normal phenotype, but remember, just because that phenotype appears normal, that genotype, they still have that recessive or that messed up allele for whatever disorder you're looking at. In sex-linked traits, only females can be carriers. Once again, that's because a female has two X's, maybe one good X, one bad X, like this situation, whereas a male, if they have a messed up X, the other Y is in good shape. So here's for hemophilia. We talked about that earlier. And here's a Punnett square to match this. You can see how half the kids get dad's X, half of them get the Y. Half get mom's good X, that's these. So both these are normal. You see that right here on the pedigree. Whereas the other half get the bad X. The girl that gets the bad X got a good X from dad, so she's a carrier. So these three right here, 75%, do not have hemophilia, although this girl is a carrier. She will not have it, but she can pass it on to her offspring. This boy that got a Y from dad now has the bad X from mom. He's out of luck because he got the bad X from mom. Unlike his sister, or probable sister, the other sex chromosome is that bad Y. So that's him right here. He does end up having hemophilia. So it's just another way to look at it. You can pause here and kind of read along and follow through with the carriers. This shows up a lot whenever you talk about, history connection. When you talk about the royal family, you've got Queen Victoria who got or contracted hemophilia probably through some random mutation, but she passed it on to some of her sons, and depending on how they married through, you pass it on and on and on and on. And then these royal families, there's a bigger pedigree. These royal families, there's the Russians here, and there's some French people over here, and it goes all over because they were marrying each other off, for political reasons, truces and whatnot. Here's the royal family in Russia. Here's, I think, Nicholas, perhaps. Not too, kind of rusty on my history, but you see how there's all sisters, and then there's one boy. He did have hemophilia. This is a con man. You can ask somebody in the history department over in the C building about Rasputin, but he was an unsavory character from history. Here's one that's a little closer to home. This is from eastern Kentucky, the Blue people. They had methemoglobinemia, and I actually have a friend whose mom was a registered nurse in a hospital in eastern Kentucky where these people would come in on a regular basis and get genetic testing and things like that. Now, not to make fun, but you can see how quite a few of these, let's just say there's very little genetic drift in this pedigree. You can see some cousins and things of that nature. So we'll just move on. So let's do some practice. All right, on your notes, you've got these instructions, and at the side, try to jot down your own pedigree to match this situation. Tom and Melinda had 4 children: Perry, Andy, Aaron, and Ellen. Perry had 3 kids with Jennifer. Their names were Rodney, Kimmy, and John. Andy was murdered with a laser by a homicidal clown. Aaron had 2 children with Aaron. Their names are Mason and Avery. Ellen thwarted a terrorist plot but died in the process. And Perry had a love child with Delilah. His name is Jimmy. So go ahead and pause this. Try to sketch your pedigree. Okay, let's see how you did. So we had Tom and Melinda had 4 kids. 1, 2, 3, 4. They were Perry, Andy, Aaron, and Ellen. Perry had offspring with Jennifer, Rodney, Kimmy, and Jonathan. Andy died by the clown. Aaron and Aaron had kids Mason and Avery. Ellen, was a hero and sacrificed herself in some terrorist plot or something. Later on, many moons later, Perry had a love child with Delilah, and they had an offspring named Jimmy. Right? Hopefully, Jimmy knows that these people over here are his cousins. Maybe he won't. Who knows? These are his half brothers. Another example. Try it again, only this time track an actual trait. So unlike this last time, here you're going to go through and you're going to color in what's probably a carrier and who's affected and who's not. So go ahead and pause it and give it a whirl.